So, a function an arithmetic function is said to have average order G, which could be possibly defined on the entire set of real numbers. So, this is said to have average order G if summation n going to n f of n 1 over capital N is asymptotic to G of n as n goes to infinity. Okay. So, here are some quick examples that we have seen in the first two lectures. So, here is the function and the average order. So, one function that we saw was the divisor function, which is the number of divisors of a positive integer n, and we saw that the average order of d of n is log n, right. Then we also saw another function which is extremely interesting to us for this course, namely the prime omega function, which is the number of distinct prime divisors of n, and this has average order we saw last time, and we are going to exploit this more today, log n. So, the average order of the number of distinct prime divisors is significantly smaller than the average order of the number of divisors. Okay. Other examples, we have these von Mangold functions. So, lambda of n picks up log p if n is a prime power and 0 otherwise. T of n picks up log p exactly at the primes and 0 otherwise, but we saw that asymptotically they behave the same, and the average orders of these functions are in fact just 1, because we saw that summation n less than or equal to x lambda of n is asymptotic to x as x goes to infinity, which is the prime number theorem. We have not proved it in the course yet, but by prime number theorem both lambda of n and t of n can be shown to have average order equal to 1. Now, here is another interesting sequence that we saw last time. This is log n over n if n is a prime, rather log p over p and 0 otherwise. This is of course closely connected with the sequence t of n, and notice, you see, whenever we try to obtain an average order of a function, it is not necessary that the average order is unique. You could have various candidates for the right hand side, but what you try to do is try to get a function which you understand well. Okay. In common parlance, these are called elementary functions. I will not give you a precise definition of an elementary function, but what it means is that you are trying to express the average order in terms of some function which you understand well, let us say powers of n or logarithm of n or rational functions of n, log n and so on and so forth, or their inverses thereof. Now, it is so suggestive to us that since this sequence itself is written in terms of functions that you understand well, turns out we worked this out last time as an application of our partial summation technique, that the average order of this function turns out to be exactly what you see. This is a nice form, okay, but proving this takes a little bit of time. Okay, another sequence that we saw, and it's extremely important for us, this is 1 by n when n is a prime p and 0 otherwise. What do you get? The average order of this turns out to be equal to log n over n. Why is this so? You had shown last time that p less than or equal to x, 1 by p is asymptotic to log x as x goes to infinity. So, this is here is your this is the average order. Now, a couple of other important functions which we have not derived, the average orders of which we have not derived in the class, but you will be able to do using the techniques that we have learned so far. So, this is a very important arithmetic function. This is the sum of divisors. So, this is defined as sum of all the positive divisors of a positive integer n. The average order of this turns out to be equal to, remarkably enough, this is zeta of 2 times n. Zeta of 2, the Riemann zeta function shows up in the average order of this function. So, zeta of 2 is defined as the infinite sum 1 over n square. In general, zeta of s for any s greater than 1 is the sum 1 over n to the s as you go from 1 to infinity. Now, another important function is what is called the Euler Phi function, or rather Euler's totient function. That is the name of this function. What does it measure? It counts the number of positive integers up to n which are co-prime to n. So, 1 less than or equal to a less than or equal to n, for which GCD of a and n is 1. And amazingly enough, the average order of phi of n also involves the zeta function, and this is equal to 1 over 2 times zeta of 2. Zeta of 2 now goes to the denominator, that is how the constant changes, times n. All right. Then you have, and this is what we are going to start off our discussion today with, this is the square of the prime omega function. So, square of the number of distinct prime divisors of n, and the average order of this function turns out to be the square of the average order of omega of n. So, this and this I am going to leave as an exercise for you to work on, and this, let us start our class today with this function omega square of n. So, what do you have to measure if you want to derive the average order of omega square of n is the following. Let us take n up to capital N omega square of n, which you write as summation n little n up to capital N omega of n times omega of n. In the last class, we saw that each omega of n is simply the sum of all the prime divisors, sum over all the prime divisors of n with the weight 1, and we have to multiply it with the same term. So, you have got finite sums arranged in a certain way, and by now you know that whenever you see multiple summations, to proceed further you almost always have to rearrange. So, what happens here, first let us just look at the inner part carefully. We write this in, we sum this up by writing it as a sum of two different expressions. First corresponds to those terms where the primes, corresponding primes you are taking are the same. So, what you are doing is, let us first take all the primes dividing n, okay, p dividing n, let us say p1 is equal to p2. So, p1 dividing n 1 plus, now you are taking all those primes which are not equal to each other, but p divides n and q divides n. However, if you have two distinct primes which divide a positive integer n, then their product also must divide n. So, to say that p is not equal to q, p divides n as well as q divides n is to say that p times q divides n. Now, the first term is something that you understand well, you actually derived it last time. This is just the sum that you have to derive in order to find out the average order of omega of n. So, this is just this is known to you. But what was this? You had derived it last time. This was actually equal to n log n plus O of n. So, you are left with the second part, which is more interesting. Let us work this out. You are running over all the primes in Q up till capital N which are not equal to each other, and their products divide n. So, let us look at the second term. What do we have? So, this bit. If p times q divides little n and n is less than or equal to capital N, you can interchange this summation by first taking all those pairs of distinct primes p and q such that their product is less than or equal to capital N, and then in this inner sum you take all the multiples of p q which are less than or equal to capital N. We used this interchange technique when we were looking at the average order of d of n as well as omega of n. So, what do you have here? The outer sum now runs over all the pairs of primes which are not equal to q and such that p q is less than or equal to capital N, and in the inner sum you have all those multiples. So, for any such pair you take p times q and consider all multiples of p times q which are less than or equal to capital N. So, all those e such that p q e is less than or equal to n, and by now you know that this is just the greatest integer function of the term n over p q. Let us look at this. So, you have p not equal to q, all products less than or equal to n, and this is just n over p q plus O of 1. So, this seems to be giving you the main term, provided you know that the error estimate is significantly smaller. So, what do you have here? All those p not equal to q, p q less than or equal to n 1 over p q plus, let us look at the error term. This will not be too difficult to evaluate. So, you have O of p running over all the pairs p and q such that the products now, whenever you have a product of two primes to be less than or equal to n, one of them must necessarily be less than or equal to root n. So, you can further write this sum as first sum over all the primes which are less than or equal to root n, and then in the inner sum run over all the q's which are less than or equal to n over p. And if you estimate that carefully, you will see you will end up just getting O of n log n here. I am just going to leave this as an exercise. Now, this part, this is a very nice sum, but you can bound it below and above by functions which have the same order. So, what you have is, you also observe this part here. This can be written as n times, you have all the primes which are not equal to q. So, suppose I were to take all possible pairs. Such that p q is less than or equal to n 1 over p q. From this you have to take away all those pairs where p and q are equal, but what is that actually? That is just summation. So, all those primes such that p square is less than or equal to n 1 over p square. And the main idea is that those parts of the sum coming from equal primes do not really contribute much. Why is that so? If you just look at the order of this term, this is, since you have p square in the denominator, this is certainly O of summation 1 over n square which converges. So, irrespective of whether you are running over all the integers n, positive integers n, or just over primes p, the moment the exponent is large enough, something greater than 1, you know that irrespective of what capital N is, this sum is going to converge, it will be less than or equal to some specific value. So, this part is just O of 1, all right. It does not matter what your capital N is here, and then there is a capital N outside. So, this is just this whole sum, because of this understanding, just becomes n times summation over all the primes p and q such that p q is less than or equal to n 1 over p q plus O of n coming from the second term plus O of n log n. So, O of n will get absorbed in n log n. So, you are left with plus O of n log n. Now, this part here, we better make sure that the estimate that we have for this is bigger than the error term. Otherwise, we will know that we have been too crude in our estimation and we will have to go back and do it again from the beginning. So, but that is okay, because you can bound this above and below by functions which have the same order. So, if you now just write summation 1 over p q, where you are running over all the primes p and q such that pq is less than or equal to n, my claim is that this is certainly less than or equal to summation 1 over p, p less than or equal to n whole square, right. And my claim also is that, you see, whenever you have such pairs of prime whose product is less than or equal to capital N, one of them necessarily has to be less than or equal to root n, right. So, if I were to take summation 1 over p, sum p over all the primes up to square root of n and square this, every term in the square of this sum that comes up would certainly be contained here, because if p and q are both less than or equal to root n, then pq has to be less than or equal to n. So, every term here is contained in the terms that show up in this sum. So, we have this inequality and every term here shows up in among the terms that come from the square of this particular thing here. So, you have this inequality on the right. Now, this is something you understand well enough, right. What do you have? You have square of, this is what we derived last time, we have log n plus O of 1 whole square, and this one, what do we have here? Here we end up getting log root n plus O of 1 whole square. But when you are looking comparing functions in terms of their orders, what do you have here? Log root n is n to the half. So, you just have log of log n over 2, right. This is just log of which in turn is log n minus log 2 plus O of 1, log 2 gets absorbed in the O of 1 term. So, this is just equal to log n plus O of 1 whole square. So, on the left you are bounded below by log n plus O of 1 square, and on the right also you are bounded above by log n plus O of 1 whole square. So, the term in the middle will be also forced to be log n plus O of 1 whole square, right. The beauty of O of 1 is that we do not have to worry about specifying the constants. We just need to understand the order of the concerned function. So, this turns out to be log n plus O of 1 whole square. Then there is a capital N here, right. So, what overall what you are getting in the end is the following: summation of n less than or equal to n of omega square of n by the appropriate change of summations and term by term analysis. This just turns out to be equal to summation n less than or equal to n omega of n. This was already there, we had put it apart, we had put it aside, plus from the part where p and q were different primes, you have derived this estimate here along with the capital N, and then there is a O of n log n as well, but that gets absorbed here. This was also, you had shown this to be, okay, let me do it in 2 steps. So, let's write this as, what do you have, n times this summation 1 by pq, which you just told me is log n plus O of 1 whole square plus O of n log n but now you had told me that this is equal to n log n plus O of something smaller, but that n log n will get absorbed in this error term here. And now let us look at what is happening to the second term. So, you have n times log n whole square, seems to be a precise term, there is no O term there. Then you have O of 1 whole square, which is again O of 1, and then you have 2 times O of 1 times log n. So, O of log n times n, which again gets absorbed in the error term that is already existing outside. So, what do you end up getting is this whole thing just turns out to be equal to n times log n whole square plus O of n log n. In other words, this is telling you that the average order of omega square of n is just log n whole square. Now, what was Turan's observation? Once you know the average order of a function, the question is, average order does not mean that the order of that function is that. What it is saying is that if you average over a collection of positive integers, then the mean value or the average value would be of a certain order. So, now the question is, how does that function deviate in that range over which you have averaged? How does the function deviate from its average order? So, in this case, what we are really looking for is the following summation n less than or equal to n omega of n minus log capital N. Now, for some values little n, this could be negative, for some values this could be positive. So, if you are just going to write this sum in this form, there would be some cancellations which will not exactly tell us how the function is deviating from its average order, and this is the reason why you have to take squares, because you are interested in the size per se, you are not trying to cancel them out on an average. So, this turns out to be, so this is what you are looking for, and this was Turan's observation. So, what is this? We already have all the tools for this. Less than or equal, this is exactly equal to summation omega square of n plus summation n less than or equal to n log capital N whole square but then you just bring this out and all you have is number of positive integers up to capital N. So, this is just n times log n's whole square minus 2 times log n summation n less than or equal to n omega of little n. It's all worked out for us. We just showed that the first sum is equal to n times log n whole square plus O of n log n then you again have n times log n whole square and then you have minus 2 times log n And what do you have in the summation? It is from our previous class, n times log n plus O of something smaller, right? I believe it was just O of n Now, what is happening is, so this O of n times log n just gets absorbed in this error term here. So, nothing to worry about there, order of the error term remains bounded by O of n log n. But the amazing thing is the main terms that you have seem to cancel out. You have n times log n whole square plus n times log n whole square. So, that is 2n log n whole square minus 2n log n whole square coming from this term here. So, the main terms are going away, and so you have this is O of n times log n. So, we do not have an exact asymptotic, but what we do know is it is bounded above square of the respective deviations for all the little n lying between, running over all the positive integers up to capital N. Okay, the square of the difference between the function itself and its expected value, so to speak, is bounded above by n times log n. This takes us to, so this was Turan's observation, and this gives us a very simple proof of the Hardy-Ramanujan theorem. It is different from the proof that Hardy and Ramanujan gave, for the simple reason that they proved it 17 years before Turan did. But Turan's proof helps us to generalize these ideas to larger classes of arithmetic functions. So, here is what the Hardy-Ramanujan theorem states. It says that the number of positive integers up to capital N for which the absolute of omega of n minus log n. So, from squares now we are going back to the original term. So, we are just, since we are interested in the size, we are taking absolute values, is greater than log n raised to some power which is a little bit greater than half. The claim is that this number is, it becomes very small as compared to capital N. In fact, it is little o of n as n goes to infinity. I hope the statement of the theorem is clear. This inequality that we just derived is telling us that on an average you can expect absolute of omega of little n minus log n to be to the order of square root of n log n. All right. What we are saying is, yes, that is what that tells you, is that the number of little n's up till capital N which deviate further away from log n to the half are very few, right. So, this is the theorem. Now, let us, once you see the proof, then the statement will become even clearer. So, what do we have here? Suppose, let us prove this by contradiction. Okay. Suppose not. What is delta here? Delta is any positive number. Let us take it to be something very, very close to 0, but positive nonetheless, however close it is. So, however close the exponent is to half, as long as it is strictly greater than half, you have very few numbers satisfying this inequality. Suppose not. Suppose something is not little o of n. What does that mean? If something is not little o of n, that would mean that it is at least the value, the size of that function is at least some epsilon times n, where epsilon is a positive quantity, right. It just stops short of 0, right. It does not actually come down all the way to 0. So, what this means is that, so that is for epsilon, for any epsilon positive, there are at least epsilon times n integers in the range for which the above inequality holds. So, for which absolute of omega of n minus log capital N is greater than log n raised to the half plus delta. So, what that means is that now if you sum up these terms over those epsilon n integers, thus summation over the entire range of omega of n minus log n whole square, it has to be greater than or equal to, since each term in the sum is non-negative, it must be greater than or equal to those, at the very least, those integers for which this inequality holds. And you are telling me here is that this number is at least epsilon times capital N. Therefore, this is greater than or equal to epsilon times n times square of omega of n minus log n, which has to be, square of this has to be greater than log n half raised to the half plus delta whole square. So, that is log n raised to the power 1 plus 2 delta. And this is a contradiction to what Turan showed, because Turan showed that this sum, so let us call this A and let us call this inequality B. Turan shows that this sum is at most of the order of n to the log n, but here you are telling me that this sum is at least n raised to a power of log n, which is greater than 1. Do you see the contradiction? So, A and B contradict each other, thus but this by a hard solid proof, we know, rock solid proof, that this is true. Therefore, our assumption has to be false. So, if at all there are some integers for which this inequality holds, they cannot be greater than or equal to, the number of such integers cannot be greater than or equal to epsilon times n for any positive epsilon. Therefore, the number of such integers is little o of n. Therefore, so this proves the theorem. Now, a nice corollary of this fact. Here, the way we have set up this inequality, we are comparing omega of little n with log of capital N, where n denotes the upper bound of the range over which they are going. But for this to be even more meaningful, we should be able to compare omega of little n with log of little n. Okay? So, at every stage in this range of integers that we are talking, how big can be the difference between omega of little n minus log little n. With a little bit of work, which I am going to leave as an exercise, and in fact in your next assignment I will give you some hints, it follows almost immediately from Hardy-Ramanujan theorem that the number of n less than or equal to n such that the corresponding inequality holds for little n instead of capital N. So, absolute omega of n minus log little n is greater than log n raised to the half plus delta, the number of such little n's up to any capital N that you take is in fact little o of capital N as n goes to infinity. So, I will let you think about how Hardy-Ramanujan theorem actually implies this. So, you can compare omega of little n with its expected value log of n, so to speak, and actually give an upper bound or give an estimate for the number of little n's for which the deviation between omega of n and its expected value is higher, is very high, and looks like it as you take larger and larger ranges, the number of such integers becomes smaller and smaller. So, now here is another question. You all know what is the average order of a function, and Hardy-Ramanujan theorem for this particular choice of a function is telling you that you would normally expect omega of n to be very close to log n. There could still be values which would be for which the corresponding difference would be very high. Okay, those would be extreme cases. So, there are the normal cases and there are the extreme cases, and you would expect in a situation like this that normally there would be a far bigger range of integers where the function would normally have the expected order. So, the notion of average order leads to two other notions, namely normal order and extremal order of arithmetic functions, which we are going to explain in detail. But before that, we want to spend some time understanding a mathematical notion which makes it easier and more transparent to state results like this. What do you mean by number of some integers up to capital N being little o of n? What does it say about what you call density of integers? This is what we want to study. Before that, what we are going to do is we want to actually, this would be a good time to start reviewing some notions from probability. So the idea is this. We want to understand certain types of densities on the entire set of natural numbers, but this begs the question about why do you actually have to define the notion of a density? Why can't you just, since we are calling this course probabilistic number theory, why can't you just take n and think of it as a probability space itself, and then just work with the probabilistic notions from on the functions that you have taken? So, this is what we want to address. So, let's start with that. So, in case, so let's quickly review the notion of a probability space. So, what is a probability space? it consists of the following information. It is a triple omega, okay, and a sigma algebra B and a function P. I will tell you what each of these is referring to, where omega is some set, or you may call it some space. B is a sigma algebra of subsets of omega. What do you mean by a sigma algebra? Quick review. That is a collection of subsets and a non-empty collection of subsets of omega which must contain the empty set. So, empty set must always be contained in this collection, which contains, so a collection which contains the empty set and which is closed under countable unions and complements. So, if A lies in the sigma algebra, its complement also must lie in the sigma algebra, and if you have a union, if you have a certain number of subsets lying in B, let us say A1, A2 and so on, then their union must also lie in omega. Is closed under complements and countable unions. For the purposes of this course, we would mostly be taking some finite set of natural numbers, and the sigma algebra that we will take would just be the power set of that. So, the collection of all possible subsets of a set. You can do that for infinite sets also. So, but this is a more general notion. So, and what is P? Now, once you have determined what space you are starting with and a Borel sigma, any sigma algebra on it, then you need to determine a function on the sigma algebra, which is called the probability function. So, P is a function defined on your sigma algebra B. It takes values lying between 0 and 1 such that P of the entire set omega has to be equal to 1, okay? And if you have any set A, its probability has to be non-negative. Okay, that is something we have already said in the definition. P is a function from B to closed interval 0 to 1, takes only non-negative values, and P of union of mutually disjoint sets in your sigma algebra have to be equal to the sum of P of n for the respective components, okay, if the a n's are mutually disjoint. In other words, P is a countably additive function. So, such a function P is called a probability measure or a probability law on the space omega comma its sigma algebra. On these spaces, you can define notions of random variables. We will come to that in a second. Let us just consider, let us take omega to be equal to the set of all natural numbers. Now, suppose I ask you, I am going to take the sigma algebra of all possible subsets of n. So, let us just take the standard sample space. Suppose I give you the following subset, let us take 2 times n. This is the set of even numbers. Or rather all the multiples of 2. I have not defined a probability measure on it, on the set n or on the probability space, but suppose we had a probability law. What would we like the probability law to do for us? What would you like the probability of 2n to be? Intuitively you would expect, or you would like it to be equal to half, because you would think, yeah, in the set of all the natural numbers, half of them are even, the other half are odd. So, you would want the probability function to at the very least satisfy this criterion. Nothing special about 2. Suppose I were to take 3 n's. This is the set of all multiples of 3. If you had a probability function on this space, what would you like ideally the probability of 3n to be? Any ideas? 1/3, right? You would expect, you know, that the multiples of 3 comprise 1/3 of the set of natural numbers. These are the intuitive notions that probability is supposed to make precise, isn't it? Similarly, for any multiple of n, a n, you would want the probability of that set a n to be 1 over a. The amazing thing is, there is no probability law on the set of natural numbers which does that. It is very counterintuitive, but this is where things start to go down south. So, here is the theorem. There is no probability law on n such that P of a times n, where a times n refers to just all the multiples of little a, is 1 by a for every a